Abhishek, sir, am I audible?
Yeah, I can hear. Hello?
Yeah, sir. Hello, sir. We welcome you to this workshop. Uh, I'll giving you, I will
Thank
give you,
you.
I'll give you a brief introduction about you, and then we can proceed with the uh, slides, sir.
Okay.
Dr. Abhishek K. Gupta, sir, received his BTech and MTech degree in electrical engineering from IIT Kanpur in 2010 and PhD degree in Department of Electrical and Computer Engineering from the University of Texas, Austin in 2016. He is currently working as an associate professor in the Department of Electrical Engineering at IIT Kanpur. He heads the Modern Wireless Networks group at IIT K. His research is in the area of stochastic geometry and modern communication systems, including 5G, millimeter wave, terahertz, vehicular, and molecular communication. He was recipient of IEI Young Engineer Award by Institute of Engineers in 2021, class of 1986 Young Faculty Fellowship by IIT Kanpur in 2022, IEEE Wireless Communication Letters Exemplary Reviewer Award by in 2016, GEFS Leadership Award by General Electric Foundation and Institute of International Education in 2009. IIT Academic Excellence Award for 4 consecutive years, 2006 to 2009. He is the author of the books An Introduction to Stochastic Geometry, published in Springer Morgan Claypole, 2022. Numerical Methods Using MATLAB, Spinger's Express, 2014, and MATLAB by Examples, Prince, 2010. Before joining IIT, he was working as Senior Standard Engineer at Samsung Research America in Dallas, Texas. In the past, he has worked in Applied Microelectronic Circuit Corporation, Pune, FutureWide Technologies, and Nokia Networks. We welcome you, sir, for this workshop. I am glad that I think people will be very much helpful with your talk. Hello. Over to you, sir.
Hello, can you see my slides?
Yes, sir, it's visible.
Okay. Thank you for inviting me for this talk and a nice kind introduction. So in today's talk, I'm going to talk about one of our recent work, which deals with how we can optimize the location or deployment of RIS in settings where there is significant blockages. So, first of all, why do we have to care about blockages? Is that in 5G and beyond, we are moving towards higher frequency communication. And for example, millimeter wave, which goes from 30 gigahertz to above to up to 300 gigahertz, is one of the prime candidates for 5G for communication. And from many benefit, it has also different type of challenges. One specific challenge with millimeter wave was that it is very sensitive to blockage. So you can see that normally in 4G, where we talk about frequencies which are lower than 1 gigahertz, at those frequencies, it was not an issue that, and you can get coverage even at inside a house, inside a room. Of course, the signal does get attenuated by buildings, but it was still okay. But in millimeter wave, these blockages are significant. And one, like for example, they can get blocked by buildings, by users, and even your own hand or the user body. And a single blockage can reduce the coverage, reduce the signal strength by 40 dB. So at these situations, the blockage millimeter wave is very sensitive to blockage. And if you want to provide good coverage, you have to find that there should be some line of sight links to give that coverage. And in case there is the link is blocked by some buildings or some dynamic blockages, we have to provide some effective solutions. What should we do when a link is blocked? For example, we can think of providing multiple links together, multiple serving base stations together, so that if one is blocked, other can serve. So if we want to use millimeter wave, because of sensitivity to the blockage, we have to find effective solution to tackle these blockages. So in that case, one of the new technology which was proposed was the use of smart surfaces. For example, here you can see that there is a base station and a user, and there is a tree in between. So the direct link is blocked. And all the walls which are around them, they are reflecting, but they are not reflecting in the direction of the mobile. So in those cases, can you develop some kind of smart surfaces which can create additional path from the base station to mobile, which were not already there? For example, these surfaces, although by directly, if you apply directly reflection laws, the link cannot be established, but these can somehow create a reflection path toward the mobile, right? So the idea was to use some kind of electromagnetic active surfaces, and that basically include man-made structures like wall, roads, or even entire buildings, which can create such path. And if these are possible, then they are the possible candidate to drive the next generation architectural evolution, right? So one such thing are now known as reconfigurable intelligent surfaces, because they have ability to reconfigure the reflections. You can create reflection in any directions, right? And sometimes we people also call it intelligent reflecting surfaces or large surfaces, right? So how do they work, right? To just give a small idea about them, let's understand how normally reflection happens, right? And how do we calculate the direction of the reflection? So if I take a simple mirror, like a simple surface which is smooth, if a wave is supposed uh, incident on this in the orthogonal directions, right? So what we first find out, what is the wavefront? Wavefront is something is basically is a plane where the frequency of, sorry, where the phase of all those are equal, right? So here you can see that frames, these wavefronts are simple planes perpendicular to the direction of the rays, right? Because if you just take any plane, all these points have this point, this point, and this point have same phase, right? Similarly, this point, this point, this point have same phase, right? Now you can see that when they are falling on the surface at the because the wavefront is parallel to the surface, also the phase of each ray when it falls on the mirror is same. For example, the phase here, the phase here, and the phase here is same. So when the wave is reflected, you can expect that on this same plane, for the reflected wave also, the phase of this, and phase of this will be same, right? So the phase basically depends on the distance the ray has traveled. If the distance is same, the phase is going to be same. So they have all traveled same distance. So at reflection also they have traveled same distance. So then the reflection is same. So the reflecting wavefront is also same, and the wave basically just goes in the same direction. If I take another mirror, for example, a convex mirror, here you can see that although the incident wave is still perpendicular, the wavefront was parallel to the surface here, but this point the wave has traveled to little bit more and here than this point. So in the reflection, this direction, the wave, because it has traveled more, the phase of the wave will be higher. So that's why if I want to calculate a plane where the phase is same, you can notice that the phase of this point in the reflection should be equal to this one, because you have to deduct this extra distance. So in that case, the reflected wave will have a diverging pattern, right? So it all depends on what is the phase when the wave is incident on the surface. For example, if the phase of this one and this one is same, they will go in one direction. If they are different, then because of the extra path it has traveled, the wavefront will be a little bit behind. Right. So you can see this example. Suppose here the wave is incident in this direction. So these waves are hitting at these different points. So the phase of this will be so the phase this wave has traveled this much distance more, so it will have a higher phase. At the reflection of, if you want to find out the points which are same, which have the same phase, you can see that this should travel less and this should travel the same distance, so that the phase should again match. Right. Now, if I somehow change the individual phases here, right, then I can change the wavefront direction and I can change the direction of the wave. For example, I can manipulate, if I can manipulate the phase of the individual rays which are falling here, I can change the direction of the wave, right? So that is the idea of the reflection surfaces, that it is made from many, it's a 2D plane made from many small reflected elements, and these reflected elements have a way that you can change the phase of the reflected wave. And by changing the reflected wave, you can change the reflection direction to any of the direction you wanted. Right. So, and these are made, the ability is given because these are made from metamaterials which have a specific property that you can control the phase of the reflected waves, right? So they can reflect in any arbitrary direction. So they act like a smart mirror, right? Not only you can change the reflection, but again, by changing the different phase, you can also change whether they are converging or diverging. So you can also use them to beamform to a particular receiver. Right. So by beamforming, you can make sure that the power reflected from all elements can reach receiver. And that's how they will give additional gains. Right. So we have seen that they can add a new part to the channel, and they can also beamform to any direction you want it. Right. And the way these are made is from using a specific material.
Sorry, sir, you can continue the session. Participant, please mute your mic. Sir, you can continue, sir.
Okay, thank you. So, right. So, let us understand how, since we are more interested in the channel towards it, let's look at them. So, basically, if you know that if you have a direct usual link, right, the wireless link, the link is affected by the path loss, which is proportional to r square in free space. For example, if your distance is r, the receive power at the other end is basically lambda square by 4 pi into 1 upon 4 pi r square. This is the Friis equation. And then it's also affected by the fading and then additional shadowing also. So total receive power will be given by some coefficient multiplied by fading into transmit power divided by r square. And if there are more scattering in the environment, then this path loss can increase or decrease depending on the environment, right? So if you look from a perspective of channel via RIS, suppose there is a user, and then there is a base station, and then there is a RIS. So the base station signal power falls on the RIS, right, which takes the signal from all these elements, and then they are beamformed toward the user, right? So basically you have, it's made from two cascaded channels. So total power through this path should be the product of the power which is received at the RIS multiplied by the power, the fraction of the power which is received at the user, right? So total power received will be given by transmit power, and L is the path loss of the distance from RIS to the base station. This is, PT is the transmit power, LDSB is the fraction of the power which is received at the RIS. Then n minus 1 square cos square theta, where theta is the elevation incidence angle, is basically the gain at the RIS. This is the fraction of power which is reflected from the RIS. And then LDUS is the fraction of power received at the user out of all the power which was sent from the RIS. Right. So the base station sent some power, RIS received this power, right? Applied some gain, and then send this signal, which again the fraction, some fraction of this will reach the receiver. If you multiply all this term, you get the total power. Right. So if I suppose ignore height, and just take a very simple case where you have a base station by blue, user, and a RIS, and the distance between base station to RIS is suppose DSB, S is RIS to base station, and from RIS to UE the distance is user to RIS, and the total distance is suppose fixed, DUB. Then if then you can say that the power is just then I am ignoring the height, so this does depend on the horizontal distances, right? So the C power will be given by just the I'm ignoring the coefficient for now because I am just focused on these distances. So the receive power will be proportional to the path loss at the first link multiplied by the path loss at the second link. And suppose the it's a line of sight communication, so the path loss is proportional to 1 upon d square. So this LDSB will be DSB minus square, and then this will be DUS to the power minus 2. This is a product of 2, right? So assuming the distance between the base station and the UE is constant, right? I want to understand where should I put the RIS, right? So you have a base station and a UIS, the distance is fixed. Now we want to put a RIS. Where should we put it so that the receive power is right? So I plotted this in a very simple way. So total R is 100 meters, and I increase DSB from 0 to 100, right? Which means 0 means RIS is put at the base station, and 100 means RIS is put at the user. So if I just plot this equation, this is the curve you get, right? And from looking at this curve, you can understand that you get maximum power when the RIS is at the user or at the base station, and you get the minimum power when the RIS is at the exactly at the center, right? If I also so in this case, optimal location of the RIS should be at the base station or at the user, right? Similarly, if I include the height also, what you get is, because base station has more height, it has little bit higher power. So it tells you that you can put the RIS at the base station or at the UE. Of course, putting at the base station will give you more gain, right? So, and again, UEs are many. So if there are many UE, you cannot put RIS at each of the user. So the better answer would be that you should put the RIS at the base station, right? But so that was the conclusion given in many of the papers, that if you want to put the RIS, you should put the RIS at the base station. It will give you better coverage, right? Now, but the problem, a significant problem is that if you put RIS at the base station, and if the base station is blocked because of building or because of any user or vehicle, then because the RIS is also there, the RIS will also be blocked, right? So in that case, RIS will not be very useful, because the main purpose of RIS was to provide a additional provide coverage when the base station is blocked. But here we are seeing that there is a big correlation between the blockage of the base station and blockage of the RIS. So if base station is blocked, RIS will also be blocked. So RIS will not be very useful, right? And so if the blockages are there, in the presence of blockages, you should put RIS in a way that it should provide you a little bit more independent channel from the blockage perspective. Right? For example, here you can see that you can put it near the base station, but you should put in a direction so that the user, so the probability that both of them are blocked together is small, right? So when base station is blocked, RIS should not be blocked, and when RIS is blocked, the base station should not be blocked. If they are both blocked together with high probability, then that location is not very good, right? So from keeping this in mind, right, we come to our main question: where should RIS be deployed? Right, we want to compute the optimal location of RIS, right, so that we can minimize the blockage probability, right, or you can say we can maximize SNR or SINR, right. So the goal will be to maximize the SINR, but I'll show from all three perspectives that what will be the optimum location. Right. So one thing you have to understand that to compute the RIS location, you have to think from a large perspective, not just from the perspective of a single user RIS and base station. You have to also care about the interference. You have to care about the blockages, which can be anywhere, right? So all this thing you have to think from a system perspective, right? So we are looking at a scenario where the base stations are deployed on along a road, right, on like a street, like a RSUs, roadside units. Then I want to deploy RIS for each base station, right? So I am assuming there are two RIS on the each side of the base station at some distance RS, and this RS distance we want to maximize. RS equal to 0 means the RS will be at the base station. RS equal to cell edge, cell radius, which means these will be at the cell edge, right? So what will be the optimum value of RS? The users are spread everywhere. The vehicle and the blockages are dynamic, right? And they are again everywhere. They can be anywhere on the road, and there can be also many roads, right? So we want to say that if we have such kind of network, where I should put the RS, right? So I want to focus on this, that there are two ways people look at the performance of a system, right? One is from an individual link performance, right? You have a single transmitter and user, you apply some modulation technique and ask what is the better rate or what is the capacity, right? Another is from large wireless perspective, where there are multiple transmitter and receivers, and then you want to ask, right, what is the interference, right? What is the probability that link is blocked? What is the network price capacity? So in this case, it actually depends on the network geometry, right? So in link, you can assume some channel, but when you talk about a system level performance, you have to include the geometry when you are calculating the channel, right? So here it's also important where you can beamform, what is the angle of each user, and all those things comes into picture, right? So the key difference here would be that we want to analyze the interference. Right? And the problem with such system is that if I just take, suppose, a single receiver, and then there are many transmitters, and every transmitter has its own receiver. I have picked the receiver of transmitter 0, and then there are other transmitter which are also receiving, so are transmitting. So from this receiver, the desired signal is coming from TX0, and the other transmitters which are also transmitting, they are creating interference. So total interference is sum of them, right? And you know that the power is actually made from path loss, attenuation, fading, all these things. So this will be for everyone. Like desired signal also will be affected by fading, shadowing, and the distance. And also the interference, which is summation of individual power, is also affected by fading, shadowing, and this one. And again, this is the distance of each link. So if there are 4 transmitters, the one is serving and 3 are interfering, you will have 3 terms for each link. You have 1 fading, 1 shadowing, 1 transmit power, and 1 distance in this calculation. And then these are all random variables. And then we want to talk about the assigner. What is the, because the performance, like the bit error rate of this one will depend on what is the assigner. So signal to interference plus noise ratio will be given by S plus I plus sigma square. And that is also a random variable. Why? Because the fading is random, the distance can be random. So all these things are random, it's a random variable. So if I want to compute the performance of this, I will have to talk about what is assigner or what is rate, right? Now assigner and rate both are random variables, so we can talk about their distribution, right? So we call it like coverage. Assigner and rate distribution, for example, probability that assigner is above some threshold, it is the CCDF of assigner. And this is also the coverage probability, which gives you what is the probability, what is the fraction of time the assigner is above some the minimum threshold, right? So if we want to compute the performance of a large network, we have to compute the coverage, right? That if I pick one user, what is the probability that this user receives assigner from the desired one above some threshold, right? Now the problem is that even if this computation is very difficult. For example, if I take very simple model, just 3 base station, the user is in between, and I want to compute the assigner, right? So now this user can be anywhere in the cell, right? So suppose it is at location X comma Y. So the signal power will be fading by distance to power A by 2. A is the path loss. And the interference is also given by summation of 2, 1. Each term will be h1 upon distance to power alpha and h2 upon distance to power alpha. And if you compute s by I, right, and you want to compute the probability that what is the probability that the assigner is above some threshold, this is very difficult to compute because this has 5 random variables: h0, h1, h2, x, and y. X comma y is the location of the mobile, right? So it is very difficult to compute, and this is the simplest model. In normal cases, you have large number of variables because you may talk about a more detailed scenario when 19 cells are there or even infinite cells are there. So what should we do in such case, right? So one is that industry basically goes for the simulation, but there are problem with the simulation because simulation cannot give you the understanding of the system. So we require some kind of analytical frameworks to study that. And if you have an expression which tells you how the coverage depends on various design parameters, then you can optimize these design factors, right? And for that, there is one tool which is very useful, which is stochastic geometry, right? So stochastic geometry is basically to study the randomness in the network, right? And you see that there is a lot of randomness like fading, right? So geometry, like the users can be anywhere, roads can be anywhere. So if you want to include all that of thing, you can use stochastic geometry, right? So we also use stochastic geometry to understand our problem, that where should we put RIS, right? So in stochastic geometry has 2 important concepts. One is, because it's the study of random geometry, one thing is, the basic thing is point. So in geometry, we first study points. So random points. If we have points which are randomly located in the space, we call it point process, right? So point process basically talks about the points which are randomly distributed. They can be uniform, clustered, not uniform. Various type of scenarios are there. And stochastic geometry provides you a way to understand or compute over these processes, right? And these points can model the nodes in the wireless. For example, they can model users, they can model base stations, they can model relays, all things you can model using the point process, okay? And one interesting point process which we are going to use is Poisson point process, right? Then let me go further. I may skip that. So stochastic geometry, you can study about some math. And the second interesting concept is, so point is covered, next is shape. So if there are shapes on the space, how do I model them? So we use some kind of Boolean model, which is basically models the configuration of random objects in the space. And for example, the set of lines, random lines, which have random length, random orientation, set of random circles, right? And how can you use them? So you can use, for example, the set of lines to model routes. You can use set of rectangles or polygons to model buildings, right? So you can use them to model different kind of objects, environments in the environment, right? And stochastic geometry has been used in various cases to understand and compute the expressions for, normal ad hoc networks, the cellular networks, the millimeter waves, sensors. A lot of places they have been applied, right? So we come back using stochastic geometry we want to use here, right? So we apply different tools, different concepts of stochastic geometry to model our system. For example, we assume that the base stations are like points on a line, right? A line is the road, and on the line there are different points which we model using Poisson point process. On short, we also call them PPP. Right? Then we assume the RIS is on the each side of RS at the fixed point. Users are again deployed randomly everywhere. It's a uniform density, again a point process. The vehicles are dynamic, are everywhere. So we model them using Boolean model. And we will also talk about roads later on. So we will again use another system which we call Poisson line process, which can model lines on any 2D space, right? So let's understand how it can actually work out. So suppose you have a base station and a user, right? And what we assume that the RAS is and the base station, they are deployed in a way that they are always line of sight, right? So you can put RAS some height so that the base station RAS link is always line of sight. And on each road, there are blockages which are distributed as Poisson point process with some density lambda v. Okay. And the height of the blockage is HV. So lambda v is the density, how many blockages are there in per meter, and HV is the blockage height, right? Now, so let's take a link length of R from base station and user. And I want to ask, when will this link be blocked, right? So if you take about the blockages of height HV and you put them, you can see that when the blockages are here, then it will not block the link. When the blockages are here, then it will block the link, right? So this length, if the blockage will fall any of this segment, then this will be blocked. And this segment is R HV upon HV. 1 second.
Participant, please mute your mic.
Yeah.
So, sir, you can continue.
Right. Yeah. So if a blockage can fall on any of the this length, which is, you can see the total length is R, the ratio is HB upon HV. So if anything falls between R into HV by HV, then the link will be blocked, right? And if there is nothing on this, the link will not block, right? So this you can compute our model, because we assume that the blockages are like a Poisson point process, which means number of the blockages in any line segment is given by a Poisson distribution, right? With the density lambda v into the line segment. So here the probability that there is no blockage is given by the Poisson probability that the variable is 0, right? So if you have a Poisson random variable with parameter mu, then probability that this variable is 0 is e to power minus mu. Okay. So similarly, the number of blockages in this length is 0. That will be given by the probability e to power minus length into density. The density is lambda v and the distance is r hv upon hv. Okay. So the probability that there is no right, is that, and probability that there is some blockages will be given by 1 minus of that. So this will be the blockage probability, right? And we assume that the user connects to the nearest base station on the same street, and we consider one typical user and we find the closest base station, right? So we can compute, actually, assuming that the base stations are random, we can also compute the probability, what is the distribution of the distance between the user and the base station. Now, if the link between base station and user is line of sight, it will be direct link, then the base user will be served by the base station. But if the link is no line of sight, then the base station will be served by the RIS, which is located on the same side of the UE. So there are two RIS on the each side of base station. So if the base station to UE link is blocked, then the UE will be served by the RIS, which is towards the user. In that case, the UE will be in outage if both of these links are blocked. Okay. If the base station to UE link is not blocked, then the RIS is not even coming into picture. Then it will be directly served by the base station. But if that link is blocked, then the RIS will come into picture. If that link is also blocked, then the UE is in outage and you cannot do that. Right. So to understand that, we have to compute, right, the probability that the base station to UE is also blocked and the RIS to UE is also blocked. Okay, so we have computed the probability, right? We have computed the probability that the link, remember, we have said that the blockage probability is 1 minus exponential lambda v hp upon hb into r. R is the link length. So probability that the base station, 1 second, give me 1 minute. Okay. Can you see my screen slides?
No, sir.
Okay, let me share again. Okay, so now I should see this. Yeah. So
yes, sir. Now it's fine.
The link between the base station and user, suppose the distance is RUB, then the probability that this link is blocked is 1 minus exponential minus lambda v hv by hb upon the distance, right? This is the equation of the probability that link is blocked, and R is the length of the link. If the length is more, the more probability to be blocked. Right, so for this one is like, now if I want to compute the probability that both of them are blocked, right, it's little bit complicated because they are correlated, right? For example, you can see that if this is a base station and a mobile and there is a blockage in between and the RIS is suppose here. So if the blockage is here, this blockage will block the signal from RIS and the base station both. So here there is a correlation. While if the blockage is on the other side, RIS is on the other side of UE, then these two links are independent, which means the link that blocks the base station will be different from the link which blocks the RIS, right? So for the cases when the UE is located on one side of RIS and base station, in that case there will be a correlation and you have to include that. So we have computed the joint blockage for the cases when the UE is between base station and RIS, then it will be just multiplication. But when the UE is outside, then there will be a joint probability that the blockage should not exist here. Right. And if I plot this, this is the equation you get. So they are not symmetric around the user. And the blockage probability gives you a very different view. It says that 0, which means the RIS is at the user. In this case, the blockage probability is lowest, joint blockage probability. And when the RIS is at the base station, then the blockage probability is highest, right? So this is different than the receive power case. If you recall, receive power said that you can put at the user or the base station. You cannot put in between. But putting at the base station is little bit better. Here it says that putting at the base station is the worst thing, because in that case it will be high probable that both of the link will be blocked. Right. So what should we do in this case? Right. So it says that you should definitely put RIS close to the base station. If you put it very far away, then it's of not very use, because most of the users will be away than RIS. The block probability will be very high, but you should not put it exactly at the base station, right? You should put it at the user, right? So the key takeaway that if RIS is placed very close or very far from the base station, joint probability is high, right? So in particular, for a given user, joint probability is minimum when you put RIS at the user. So you should put, from a particular user perspective, you should put RIS at the user. But now there is lots of users, right? And suppose you have only one RIS, then where you should put. So the idea is that you should select a location of RIS which results in the smallest blockage probability, or for an average user, or for a user on the average, right? Which means that you have to now average over the user. So we know the distance of the base station from user. We know the distribution. So if I integrate the blockage probability with the user distance, I get one equation, right, which I can compute, right? And this is a function of two important parameters. One is the severity of blockage with respect to base station deployment. 1 second, give me 1 minute. Sorry. So it is important. Basically, there are two important factors. One is ρB, which is the severity of blockage with respect to base station deployment. That the ratio of mainly the blockage density and the base station deployment, which means how many blockages are falling per respect to the base station deployment. And second is the severity of blockage with respect to the RIS deployment. Right, so this is only a function of these two variables, and right, so we can compute this, and we have plotted this. For example, if I plot, then what we can verify also, that if you have RIS deployed at very close to the base station or very far, then you will have high joint probability, and there is an optimum value where you should put the RIS. And we have found out that this optimum value of RIS, the distance between RIS and base station, is of the order of R, right? Which is cell radius, right? So basically it's of order of the cell radius, which means that you should put somewhere in the cell. Now, where should we exactly put? It depends on the blockage severity. For example, if you have less blockages, if you have small amount of blockages, then mostly the links which are close by, the user which are close by will not be blocked. Only the user which are far away at the cell edge, they will be blocked. So you should put the RIS near the cell edge so that you can provide coverage to the cell edge users. In that case, the optimal distance of RIS to base station comes out equal to the cell H. But if the blockages are very severe, in that case, even the small nearby users can get blocked. In that case, you should put it somewhere in the middle of the cell. So it goes more towards the cell radius by 2 distance. Okay. And we can actually write down the equation. We can even solve it, and we even got like a equation that what will be the optimal value of RSO, which is given by this equation. And then we can even find the approximate solution, which again gives you in terms of the blockage severity, right? 1 upon lambda b, 2 upon rho b, rho s plus 2. 1 upon lambda b, 1 upon lambda is basically cell H, right? Cell radius. So lambda b is the blockage density. 1 upon lambda b will tell you how far each cell radius is. So 1 upon lambda is the cell H, cell radius. And it's a fraction of that, right? If the rho b and rho s is very high, then it just decreases. But if rho b and rho s are small, it goes close to the RS. So the 1 upon lambda b. So this is what we get. Right. So using stochastic geometry, we can actually compute the optimal RIS location, and we can give some insights over that. Right. So this is just from the perspective of from the blockage probability. Now we can include the other effect. For example, first of all, we can include the effect of receive power also. Right. So we can compute something called signal to noise ratio. So if the base station is directly linked, you have some signal strength. And if the base station is served via RIS, then you have another equation which include the path loss of the two links from base station to RIS and from RIS to the user. So these are two things. And of course, if you are not blocked, the base station U is not blocked, this is the signal strength. And if the base station is blocked, but the RIS is not blocked, this is the signal strength, right? So you can compute the coverage probability, right? And then now you can see that here I have plotted the receive power, right, which says that you should put near the base station. And the blockage probability said you should not put near the base station. So if you multiply both of these factors together, you get a trade-off between the two, right? So you still get an optimum RS position, but it is some little bit different than what you got from the blockage probability, right? So here also we can compute the probability distribution of SNR, right? And again, this will be has two important terms. One is when the link is not blocked, then you have the SNR will be from the perspective of direct link strength. And when the base station is blocked, when the RS is not blocked, then the signal power will be towards via the RIS. And when both are blocked, we don't get any coverage. So we have computed this. We are able to find this equation again in terms of the blockage severity and the lambda b density. When we plotted this, we can again verify that if you put RIS near the base station or very far away than the base station, then the coverage will be small, and then there is an optimal location of RIS where you should put, and that is also of the order of R, right? And we get very similar insights also even when we include the signal power, that when you have blockage severity high, then the optimal will be nearby in the cell in the middle of the cell. When the blockage severity is small, then the RIS is usually should be put at the cell edge, right? That's one thing. And we also plotted the effect of at what height, right? So height also has same thing. If you increase the height, then the blockage probability reduces, but the signal power also reduces. So when you have this trade-off, you get again an optimal height where you should put the RIS. Okay, right. So that was from the perspective. Now I can also include the effect of interference, right? Because if you put towards the cell edge, right, it's going to interfere more to the other cells. So for interference, I have to again compute the interference from all the points, right? So interference will be coming from all the base stations which are not blocked. Then the interference will also coming from other RISs which are also radiating energy in the same direction. Right. Right. So again, I will not go to the complete detail of this derivation, but that it was also challenging because again there was again correlation in the blockage. You can see that if there is a user and then there is a base station in one direction, if that base station is blocked, then all the other base stations which are after it will also be blocked, right? Because they are in same direction. It cannot happen that a nearby base station is blocked, but the base station after them is unblocked, right? If something comes in between, it will block all the signals beyond that, right? So we basically have to compute this by keeping in mind that correlation also. So we have, I'll skip the derivation. We have condition on the closest blockage on each side. We have computed the interference from all the base station from both sides of the user. And then we computed the distribution by computing the Laplace transform. All of this we can do using the tools from stochastic geometry. Right. We also compute the interference from the RIS. So if there is a RIS, it will also reflect the signal of your desired base station and every other base station also. So they will also fall into your direction and they will interfere, right? So they will also create some interference. We have computed that, and then we can compute coverage probability. We include all the terms, right? It include all the interference terms. It include the distribution of the closest blockages and the distribution of user to base station distance, right? And we again plotted it. So this is SNR and this is SINR with base station interference and RS interference. And we saw that if I also include interference, the optimal RS changes slightly, right? Which means that it will reduce because when you include interference, if you put RAS far away from the base station, it will also affect other cells. So it gives you a little bit more motivation to put the RAS in middle of the cell, right? So when I include all the three effects, that the joint blockage probability, which says that the RAS should be put on the average, right? And then I include the effect of coverage, signal strength, which says that it should be put more toward near the base station. And we also add the effect of interference, which says that you should not put it very far, otherwise it's going to affect the other cells. If I include all three effects together, we get a optimal RS location, and which is somewhere in the middle of the cell, right? And which can be computed and given, right? A similar thing can also be computed from the perspective of height also, that there is an optimal height where you should put, right? So, right. So this is all about where I should put RIS. Hope that should be clear. When you have a single road. Now we usually don't have just single road. We have multiple roads, right? What should we do in that case, right? How do I model multiple roads? So usually network is spread over multiple routes that can be irregular. And for example, if you look at one city map, you can see all these roads crossing each other and they're randomly distributed. So if you put base station along each of the line, right, how do I go about that? So there are different models which you can use, right? I have mentioned some of them: random planar graph, right? Poisson-Voronoi translation, Poisson-Delaunay translation, and Poisson line translation. There are different many other models, even more models like Lily-Pond model and everything, which you can use for multiple, right? One of the easiest one is something called Poisson line process, right? Poisson line process is very simple. It says that you can model them as a set of many lines which are at random distance and random orientation. Right. So how is the distribution located? So every line can be, if you remember, every line can be represented by the distance rho and the angle phi. Right. So if I make a separate space, right, here this is a different space. This is a 2D where the lines are located. This is a different 2D space which on the x-axis has the angle orientation and in the y-axis it has the distance. Then this line can be represented by a point phi p rho comma phi, a single point. So if you have many lines, each line can be represented by one point, so they can all be represented by a set of points. So Poisson line process says that if these points are located as a Poisson point process, PPP, then the corresponding line process will be Poisson line process. So we use them and we use them to model the roads, right? By changing different orientation distribution, you can get different type of distribution. For example, here on the right, you can see something which can model downtown or city type networks where there are more regular oriented roads but at a random location. And the first one is where the orientation of the roads is also random. Right. So we use this and we compute the effect of them. So in that case, one of the important factor is that if you have given an option to put the RS at the road or at an intersection, what will be beneficial? Right? If I only have one RIS, if I put them at the intersection, then you can serve two roads. Right? So taking motivation from that, we also compute the effect of RIS when they are mounted on the intersections. Right? So we have taken all these systems and all these different roads and we computed the intersection. We put RAs on those locations and then we also compute the effect. So in this case, if you are blocked from the same RAS, then you can, if you are blocked, if a user has its base station blocked and also the RAS is blocked, then if the base station is blocked, then all the other base station will also be blocked. So in that case, what it can do, it can take this from a base station on another road, which is crossing it via the RAS at the intersection. Right. So here the RAS at the intersection can be used, and we add third term when the base station is blocked, when the RAS is blocked. In that case, you have one more point of coverage via a base station on different road which is intersecting it, and that signal you can receive via the RAS point deployed at the intersection. Okay, so we also include that, and we again compute the joint probability that even this is blocked, and then we say that compute the probability that even if this is blocked or not blocked, what is the additional coverage you can get. And if you also include that, right, we can get some kind of coverage benefit. For example, I plotted here with respect to two different system kind of scenarios, and you can see that this dash one is without any intersection, and then this other two curves are with intersection, and you can see that with intersection RIS you can get better coverage than the two. Right. So that is basically what was the goal of this talk, right? So what I wanted to first tell you that what is RIS, right? Is basically a way that you can create additional path, right? But the question is, where should I put RIS? There are many base station, many users. So from a single base station perspective, where should I put its RIS, right? So it is serving many users. So one thing is we can put it where it should minimize the blockage probability when the RIS is used, right? So RIS will only be used when the base station is blocked. So you should put RIS somewhere, whether it gives you a little bit independent blockage, right? So we say that you should put it nearby to the user, and because there are many users, you should put on an average user. And in this averaging, it is important which are the users which are blocked. So the users near the cell edge are usually blocked, but so you should put near the cell edge. But if the blockage is severe, then the base station, all the users can be blocked. You should take an average and put it there. Right? Then we include the effect of signal power also, and then we also include the effect of interference, and we compute the optimal distance. Okay. Third point was, then we also say that their intersection, you can also increase little bit coverage more by putting the RIS at the intersection, because now they can serve two different type of users, right, on both streets, right. And another goal of this talk was to make you understand that when we talk about the deployment problem, or from then we require a study from the system level perspective, right. When you talk about whether something doing something in a network is good or bad, you have to talk from the more system level perspective. And in that case, you uh, the problem become very complex, because you have to think about all the interference, all the blockages, and different network parameters. So what is a tool? You can use stochastic geometry tool to model such things. And stochastic geometry provides you a very nice way to model nodes, to model blockages, to model coverage. And using these models, you can calculate, get an expression, and then from expression, which gives you a very good idea how the coverage depends on various parameters, you can optimize them, and you can get very good design insights from them. Okay. So that's all from my side. I'm open to questions if you have any.
Thank you, sir.
So
Thank you
I'll
for
just give you I'll just
Yes,
give you references, that these are the references, and I can share this. You can we have written a paper on this. You can read the full paper also if you're interested. And maybe I can just give you a small 2-minute this one also, that as a group at IIT Kanpur, we do different kind of research. Like, for example, up to now, we have been working more on 5G research, which is like current, where we have talked about stochastic geometry, which can be applied to ad hoc networks, device network. We have worked on vehicular communication, millimeter wave spectrum sharing. We also worked on cyber physical and broadcast. So all these places we worked on understanding them from more system level perspective, computing design insights. And as we go beyond, we are trying to understand how different new technologies are coming in. For example, RIS, as we talked about in today's class. We have also worked on the analysis of terahertz networks, satellite communication, right? And we also work on very interesting topic called molecular communication, which is a study of communication via molecules. It's very different than traditional RF or wireless communication. Here you send molecules to send some information exactly as it happens in our body. So we work on different system level perspectives on that, right? So this is my group, and from IIT Kanpur, and hopefully you like the topic. So yeah, sorry. So that's all from my side. I'm open to questions.
thank you, sir. Thank you for the wonderful sessions. Participants, if you have any questions, put it in the chat box. We'll take it from you. Sir, I'll repeat the questions from the chat box. Signal strength decreases as the number of RIS increases. Sir, first question, signal strength decreases as the number of RIS increases?
Not necessarily. No, I mean, if you increase number of RIS, then usually you are increasing the area of the surface. In that case, you are getting more and more power at the, if you can configure this one correctly, then you can get more power at the receiver. Right. The problem is that as the number of RIS, number of elements in the RIS increases, then you have a problem. Right. But again, I think you meant number of RIS, okay, not the element. Right. So if you have multiple RIS, then still there will be some interference from the RIS. But we have shown that the interference of RIS is not much. Right. So in the usually descent limit, which we have talked about, the number of RIS does not put exactly much effect on the coverage.
Sir, moving to the next question, how deployment and distance between the RIS affect it?
Sorry, say it again. How?
how deployment and distance between the RIS affect it. Means they want to say that like RIS placement and the distance between them affect the signal strength.
Yeah, so I've talked about that. Normally, in a single wireless link, the as you increase the distance, the signal strength goes as d to power minus 2 or d to power minus alpha, right? Because of like in a free space, the wave basically expands, so the power goes as 1 upon d square. In other scenarios can further go, but in RAS case, you have two links. One is base station is sending power to RAS. RAS is collecting that power, applying something, and then sending it back to the sending into the user. So now you have two different links, and the power will be basically multiplication of both links. If you increase any of the distance, the power will basically increase. Right. So if you double this one, now there's a problem that is 1 upon d1 square into 1 upon d2 square. So if you double all of them, then it will actually goes 1 upon 4, not 1, I mean 1 upon 2 square into 1 upon 2 square. So it is very sensitive to the distance. If you increase the distance, the effective path loss will be not just alpha, it will be 2 alpha.
Okay, sir. Moving to the next question. How does the design of meta surface affect the efficiency of RIS in mitigating the blockages?
Right. So the implementation part I have not talked about. Right. Again, in RIS is a little bit futuristic technology. So there's a lot of work being done, and still people are trying to demonstrate various systems. Right. The efficiency and other things are there. Right. So again, if you are not able to beamform properly, right, if you're not able to configure them, then again it will create more and more interference. Right. I have assumed here very nice interference pattern where RS is idle and only it can interfere in a particular direction. But if your RS are not very efficient, then the interference will be large, because in many cases the signal power will be spread more. So in that case, you have to worry about that if you put it more towards the cell edge, it's going to destroy other ones. So you have to literally worry about, and also you have to worry about how many RAs are you going to put. So right, that also going to increase the interference if the configuration of phases is not properly done.
Okay, sir. Moving to the next question. Give me any suggestions about performance analysis using spatially correlated channels.
Sorry, can you repeat again?
Yeah, give me any suggestions on performance analysis using spatially correlated channels.
Okay, so in this study we have talked about this correlation. When I say blockages, I mean large scale fading. The large scale fading does have this correlation we have included, right? That if the two links are close by, they will be both blocked, right? So that effect we have included. Now there is like further thing you can include that effect of more shadowing and those terms. Right? It's a little bit difficult to include the spatial correlation in the stochastic geometry study, but there are few papers which can talk about that.
Okay, moving to the next question, sir. Instead of multiple RIS, is there any other solution? That means, can we use drones? Something like that they are asking.
Right. So you see, think about this one. RS is what? RS is mainly a type of relay, right? So if you do not get direct connection, you can use a relay to send the signal, right? Now the problem is, of course, there are different type of technology has been proposed. You can use traditional relays, you can use drones, right? You can use other method, but they are all active devices, which mean you need power for them. You have to spend some money on them, and you have to continuously repair them. RS was proposed in original manner as a passive device, which you can put, and it doesn't require a lot of power, right? It can usually just reflect the signals, but the configuration can be done so that it can reflect in a particular direction, right? So definitely there are many other ways people are talking about, like and many are being used also. Many places you have seen relays which can extend the coverage. Right. Here the RS idea was to create a more power efficient device, mainly passive, so that it may reduce the cost in the long run.
Okay, sir. The participants, if you have any questions, try to type it in the chat box. We'll take it for you. That's it, sir. There are no more questions. I'm Swarnima. I'm handing the session to you. Swarnima, are you there?
Hello.
Yes, you
Yeah.
can continue.
Yes, thank you. Thank you, sir, for that wonderful session. I hope your insights have added to the immense value to the participants' understanding of the topic. We appreciate your time and effort, sir. Thank you so much for joining in.
Okay, sure. So I have shared the link, and it's also available on my website as a preprint. If you're interested, you can go through the paper and read more. And if you have any question, you can definitely email me. Right. Once again, thank you for inviting me, and hope you had learned something from this.
Yes, sir.
Okay,
We will put
thank
up
you.
the email ID and the paper links and everything on the chat box, sir. They can contact you if they have any queries about.
Sure, thank you. And everything is available on my website. So you can just point my website also. I mean, you can just type in my name and you should get my website, and here you can find all the papers.